Now we quickly move back to JSON, and with the increasing pressure on XPath, I guess you're going to make some connections between XPath, JSONPath, and the upcoming XQuery 4 standard.
We're going to implement JSONPath and XPath. Well, XPath, XSLT, and especially with Invisible XML. So,
Alan Painter.
Thank you. I wanted to explain just the title, why I said with an invisible friend. So obviously it's Invisible XML, but really I'm thinking about Harvey. And since the very beginning that I've heard about Invisible XML, I've always thought of Harvey. So Harvey is a 1950s film and a play. It's an American play. And Harvey is a giant invisible rabbit. And we never see him, even though he's a subject in the film. But his Elwood is, Harvey is Elwood's invisible friend. And so Elwood takes Harvey everywhere. And I've always thought that Harvey was a metaphor for Invisible XML. And that's because when Elwood goes out for drinks, he brings Harvey, he introduces Harvey to his friends. And his friends just think, well, he's kidding me, or well, they can't say anything, so he must be a little eccentric, or maybe he's even a little bit crazy. But then some of Elwood's close entourage, they discovered that, in fact, Harvey is real. And in fact, he's very powerful. He can even stop time. So in some ways, I've always seen the Invisible XML crowd as being fairly eccentric myself. And I didn't even think about using Invisible XML originally for implementing JSONPath. But when I did try it, then I did discover it was very powerful. So in this way, I think that Invisible XML is my new invisible friend. So JSONPath, I talked about it last year at XML Prague. JSONPath has been around since 2007. It's been very widely adopted in the industry. There's over 50 implementations in 20 different languages, and they all produce different results because there's no standard. And so a group of JSONPath people with the IETF, the Internet Engineering Task Force, they decided that they were going to set things right, and they came up with a standard. It's a proposed standard as of last February 2024, rather. And so I was talking about this at XML Prague, and I saw this as an opportunity because so now we have this new standard. We didn't really have any implementations of it. And I thought, well, okay, let's go ahead and make a good implementation. And I thought this is a good opportunity to showcase how XSLT and XPath, and well, there's no XQuery in it, but it could be, how they handle JSON really well, and also how they handle these complex processes really well. And I thought there's some features in here that would be really useful to be able to use and showcase. And then also the heart of the entire standard is an ABNF. It's an augmented Bacchus-Naur form grammar. And I know that Stephen has a paper about how IXML can read augmented Bacchus-Naur form grammars. Now, we're not going to read theirs. We're going to make our own, but it's very close to it. So I thought that as the heart of the implementation, that worked really well. And then I've always been interested in how specifications become implementations, how a standard becomes an implementation. So I wanted to see about how we could make an implementation that's close to the standard, maybe discover something about the standard from the implementation. So the name of the implementation is AJP. It's for a JSONPath processor. It's also my own initials, so I feel very close to it. I meant to put this in GitHub, and I didn't. I mean, I meant to put it in the chat, but I didn't. But it's under GitHub, XML Jacquard, AJP. It's also in Maven Central. You can import it as a Java module, and there's a little Java API to run. The implementation runs all of the compliance tests. It does that when you run the unit tests. And there's almost 700 of them in the standard compliance test today. And so all those run correctly. And then also the consensus test runs. In terms of implementation, it's about 1,600 lines of XSLT, 200 lines of Invisible XML. So what do we have to do for JSONPath? It's a query expression. We have the processor that's going to read it. It's then going to apply that query expression to a query argument, which is in JSON, and that's going to produce an output node list. So a node list is not really in JSON, but it's It's a list of tuples with a string that corresponds to a normalized JSON path, which tells us where that value is within the query argument, and it's also the value. And some of the elements that are in JSONPath queries, there's identifier segments and selectors, two identifiers that are only used within the filter selectors, except the dollar identifier is always the first character in any JSONPath query. It's the obligatory first character. And following the dollar then is a series of segments, could be 0. And those segments themselves have at least one, but maybe more selectors within them. And so there's 5 different kinds of selectors, not 6, 7, just 5. And the filter selector is the interesting one because it's an arbitrarily complex Boolean expression to say whether or not we select that node based upon the result of the expression. And so AGP is, I think this is really standard. It's a 3-phase process. We've got IXML, which is going to read the query expression. It's going to produce an XML document output, which is the abstract syntax tree. I'm using Norman Tovey Walsh's the 9ML, it's coffee sacks that I can call from XPath. And then we're going to use XSLT to produce a description of the query expression. It's actually going to produce it as a series of singleton maps. And then, so with that description then, in the third phase, we're going to apply the description to, and we can apply it to repetitively to multiple different JSON query arguments, and we'll produce that output node list. And so I've got the 3 phases encapsulated in 2 XPath functions. So one's called get segments, so you pass it in the query. It gives you the segment description. We'll look at that in a second. And then the second one, apply segments. Well, it's going to take the segment description, and it's also we're going to pass in whatever JSON value we want to evaluate with the JSONPath processor, and we'll get the node list output. So let's take a look at those 2 main data structures, and we'll see them. They're used over and over within the implementation internally, but also in the external calls. So the segments it's a sequence of singleton maps with a string key that says, well, is this a descendant or a child segment? Those are the 2 possibilities. And then the value is going to be one array, in a sequence of arrays, one array for each selector, which is in that segment. And then those arrays have 2 functions. We'll look at that in a second. And so the output node list, but it's also used for input. It's also used as an intermediate means of doing expression evaluation. The node list is also, it's a series of singleton maps, a sequence of singleton maps with a key, which is a string, which is the normalized JSONPath expression of the value of that, that corresponds to that value within the query argument. And so I mentioned that it's arrays of 2 functions, one for each selector. So essentially for each selector, we're going to have a function keys, and the signature for it says at runtime, we're going to provide it the item, which is part of the query expression, and it's going to produce an ordered series of keys. And so one of the important things is, for instance, for the slice selector, so that's going to give us the values of at different indices within an array, within a JSON array. The slice selector might give us those indices in the inverse order in case the step is negative. So, so the keys is really going to determine the order of the output. And then the test function is going to give us a Boolean value to tell us whether or not we should include that node within the output node list. That takes 3 arguments. One of them is the root, which we always pass around. Now, it turns out that the test function always returns true, except for the filter selector, but all the other selectors, it's always just going to return true. So this is the structure that we're going to use to describe in this segment's description the entire query. And so when we're doing the segment processing JSONPath, one thing to know is that the way this works is that we've got a series of segments. Each segment has selectors. We're going to produce an initial node list, which has just the root in it. It's just one node and it has the whole root. And then in the first segment, then we're going to present that node to each of the selectors in order. It's very important that it's in order. And then it's going to produce an output node list from the first segment. And so we can see here we had 3 selectors, and each of those produces one value, our one node output. And then that becomes the input to the second selector, to the second segment, which just has one selector. And in fact, it only chooses one value, the 23, from that middle output node. So this is how the input of the previous segment, the output of the previous segment becomes the input of the previous segment, the next segment, until you've gotten to the last segment, and that's the output of the query. So that's how JSONPath works. So we're going to look at a little code. What I'm hoping is that you're going to see, sorry about the code, but that this is really simple. And I think in a way the code sort of describes the whole JSON mechanism, maybe even better than the specification, I don't know. So when we're doing the evaluation part, we already have segments that have been generated. We're applying it to the JSON values. We're going to call apply segments. There's a 2-argument version where we pass in the JSON root, and then we pass in the segments that we've generated from the expression. And it's going to generate the initial node list. We said that the initial node list has just the root in it. It's a single node in that node list. And we're going to pass that down to the 3-argument version of apply segments. And that's going to return the node list of evaluating all the segments. And there's just one last thing we do. We're going to do convert nulls here. And that's because, well, I said that the node list always has JSON values in it, but every once in a while it has some XML values in it. It has some elements. So what we're going to do is, in case we have a null element, this $null, as one of those values, we're going to replace it with the empty sequence. We'll see why we do that. So this is essentially priming the pump with that initial node list. And then when we get around to calling the 3-argument version of apply segments, and we're always passing in root here, this is where we say, well, if we don't have any segments left, then we'll just return the current node list. That's the final result of the entire query. But otherwise, what we're going to do is we're going to generate a node list that is a result of the selector processing for this particular segment. So we're going to pass the selectors from this segment into either children or descendants, depending on the kind of segment. And we'll get that node list as a result, and then we'll call apply segments, the 3-argument version, recursively on the remaining segments. So this is how the output from the previous segment becomes the input to the next segment. So then we need to look at children and descendants. So we still haven't seen any of the functions from the selectors being called. We're going to see that called here. This is the only place where we call the functions in that selector, that array that's associated with the selector. So this is where within RFC 9535, the standard, it says that we need to pass each node in review in the input node list. And then what we'll do is we need to apply each selector to it. So that's where the selector and selectors, that's going to give us the array. And then we're going to call the first function in the array, that's the keys function. And we'll get the list of keys that correspond to that selector and to this node. And then we're also going to generate a path. So this is the location. That's really what we're doing, is we are concatenating the value of the current key onto the path, onto the parent path. So we're augmenting that path a little bit to describe the location of this child. And then this is where we're going to decide whether or not we have a node output. This is where we generate the singleton map with the location and the value at that location, but only if the second function in the selector is the test function returns true. Now it returns true for all of them except for the filter selector. We'll see how the filter selector has a different mechanism because we have to evaluate the expression that goes with it. And just one other note, so here we have this $null, and that's because if the value here is null, what that means is the empty sequence rather, what that means is we've come across a literal null in a JSON value. And we can't really describe it as an empty sequence, so we'll see later why. So we're going to use this XML value here, this XML element value, this $null, to hold its place. And this is the one that we replace with the empty sequence when we do return at the first 2-argument apply segments call. So this is how we generate all the output nodes using the children function. And the descendants function, so descendants are a bit like a descendants axis in XPath. This is where we're still going to call the children function to generate the output nodes, but we're going to do recursive calls to descendants, which will then again call children on the grandchildren and on the great-grandchildren. So then we're going to go through we're going to go down the different values in the node list. And so we're not calling the selector functions here because they're only being called from inside the children function. And I mentioned the path function. So this path function is just, we're taking the path of the parent. It's already been constructed. And then we're going to add the square braces that correspond to the canonical segment. And then if it's a map, then we're going to put a key between single quotes, a string key between single quotes. If it's an array, then we're going to have an integer here for the array. And the integer is 0-based, so we have to subtract 1 from the XPath version. So that's it, actually. We've seen all of apply segments. It's just a handful of functions. I think it's pretty simple, and I think that it's actually a simpler description of what's happening than even what's in the specification in RFC 9535. Apply segments doesn't have any errors, by the way. Any errors that you run into are going to be in get segments. So what I've tried to do is say that we can motivate the use of segments with that structure by seeing apply segments. So let's go ahead and look at how we generate the segments. Oop. There we go. All right. And so the first phase is where we're going to use IXML to generate the abstract syntax tree using Norman Tovey Walsh's 9ML, which is coffee sacks as well. So here's an example of one abstract syntax tree, the first part of it, that's produced by this expression. To show, this is the augmented Bacchus-Naur form version from the specification. And then above it, I've got the IXML. Now, it looks a little bit different from Stephen's IXMLs because I used equals as a separator. That's a possibility. And then I used, for the alternatives, I used the vertical bar because it looks closer to the slash that's used in the IETF ABNF. And then you do that too. There we go. But they're really pretty close. So these are the top 6. You can see I don't need the root identifier serialized, so we've got some minuses in there, and also for some of the other terminals. But really, it's very close to the original ABNF. I think that somebody who is used to seeing ABNF would not be surprised to see what is happening here. And then this is the entire get segments mechanism. So we've got a parser that's been generated. It's a function generated by Coffee Sack's load grammar, where we're loading 200 lines of XML. The original is about 150 lines, and so, but I added a few more lines. I spaced it out a little bit too. The get AST for get abstract syntax tree, then it's just going to call the parser, passing it the string, and we're going to get the XML document output. Now, in case there's an error, then we're going to get an XPath error here. So then we won't have an XPath document output. We have to deal with the error separately. But I won't go into the error handling. And then the get segments part is simply apply segments on that document. So I think this is, obviously that means that everything is XSLT driven once we have the AST generated. So, and the XSLT is pretty simple too, because, so here's the top levels. Remember, we're producing a sequence of singleton maps with either child or descendant in the string, and then we've got that non-empty sequence of arrays of functions for the selectors. And so these are just going to call recursively apply templates, so we're going down through the grammar to generate. When we get to segment, then we do have a single map rather than a possibly empty list of maps. So the things that generate segments, there's 3 templates that generate the map that corresponds to segments. So it's either with a key child or descendant. So it is a singleton map. And then we're going to do recursive apply templates to generate the values for those maps, which is, once again, those arrays of functions. All right, and so then we've got 6 templates that generates those array of 2 functions. So we can see we've got an array constructor, and we either have a named function reference here, or we're doing partial function application. For the test function, which is the second function, we're always using wildcard selector test, which returns true, except for the filter selector. For the filter selector, we're going to generate the test function by recursive apply templates as well. So I want to look at that partial function application because that's really vital for this whole mechanism. So here's, for instance, here's the slice selector key function. It takes 4 arguments, but we said that at runtime, we needed to have a function that just takes 1 argument with the item. So what happens is the item is available at runtime, but we get the start, end, and the step from the query. So what we'll do is we'll do this partial function application with the start, end, and step. So that's going to bind these values, which are possibly empty, to those 3 arguments. And it's going to produce a result argument that has a result function, the partially applied function, that takes that single argument, that item that are separated by the space. So essentially, the last 3 are the compile time arguments, and they're captured, like I say, it's captured by partial function application at compile time to provide a result function that's going to take a single item at compile time, at runtime. And that item is going to be coming from the query argument that's called with apply segments. So here's partial function application for a keys function, and it's similar for the index and the name selectors, but with just 1 argument. It's just either the integer index into array, or it's the string key of a JSON map, a JSON object. We also use partial function application for the filter selector. So this is for the test function, which takes 3 arguments. The third argument is always $root. And so here we're going to be chaining functions. And so I'm trying to explain what I mean by chaining. So we can see here in the grammar, we've got a comparison expression that has 2 comparables. So we're going to supply those as, they're going to generate functions as this operand variable. And then the comparison op itself is going to be, it's just going to be a string. It's equal or not equal or something for the comparison. And then we're going to call the comparison expression with partial function application in order to capture those functions that have been returned by recursive apply templates, and also to capture the operator. And so we can see that we're calling a function. We're generating a function that has that test function interface, and we're chaining functions that we've created further below. So just to give an example of chaining, so for this XPath JSONPath expression, we've got some sub expressions in there, @.a and @.b. So that says take the current node and take the value of A, or that's the current node value of B, and then that's going to supply that as the function argument for the function length. So we can see that the comparison expression, we're going to capture via PFA these 2 operands. One's the singular query, and the other is this function expression. And they themselves are going to have, like for the function expression, is going to have arguments. For the singular query, there's just going to be this call to apply subsegments. In fact, both of these call apply subsegments. And this is where I think it's kind of interesting, because what we're going to do is we're going to represent the sub-expression as, once again, as segments, as this sequence of maps that are either child, and then also has this array. And what we can do then is we can call apply segments on these subsegments. So that's what apply segments is going to do. So we're going to, by partial function application, we'll capture segments and this relative flag. This relative flag really says, is that sub-expression, does it start with $, in which case it references the root, or does it start with the @sign, which means that it references the current node? And we're going to use that to populate the initial node that we're going to pass, like we did at the very beginning of the evaluation phase, to apply segments. And we're going to put either the current node or we're going to put the root node in there. And this is the only place where we use that root argument that gets passed all over the place in all these test functions. So these are all chained together. It can apply subsegments. These are going to, we're going to return node lists, and we're going to use the return node list in the comparisons. So that's really how a partial function application allows us to capture information that's available at compile time, and then have it available in those partially applied functions that we're then going to call at runtime. So most of the mechanism within JSONPath is really driven by the grammar. But there's a few places where the grammar is more general, and we have to look at some specific cases. So here's one case so we saw that there was a length function that was called with a query, with a filter query. So what happens is that functions can have arguments of different types. They can take a single value type. They can take multiple values. And we need to look, depending upon the function, what type that it's producing. And so this case where the argument type is a value type, that means that it has to be either an empty or it needs to be a single value. And so the grammar doesn't handle this for us because the grammar has to be more general for all the possible function type, argument types. So when we get around to doing the partial application, before we can do it for this singular query, we need to check to make sure it really is, the specification tells us it needs to be a singular query. And so we've already generated the function that's associated with the query by recursive apply templates, but we're going to go back and also check to make sure that filter query really is a singular query. Now, in order to be a singular query, it needs to be a single, all the segments need to be child segments. It needs to be a single selector per segment, and it has to be a certain subset of different selector types. So we can apply this here. So it's actually kind of nice to be able to see this in the templates because function argument filter query is different from function argument, which could be a literal, which could be function argument, could be another function call. So each of these has its own rules, and we have them split up into different template matching. And I think that reads really well and really closely to the specification. So I mentioned that sometimes we have some XML values in the node lists. And here's the two values. There's nothing and null. And so nothing is really, is one of the values. They don't really tell you how to manage it. But within the specification, they tell you that a value type is either a JSON value, but it's never empty. It's either a JSON value or it's nothing. And so nothing is different from an empty sequence. And certain functions, so for instance, the length function, if you call it with a JSON literal null, for instance, it doesn't return 0, it returns nothing. And then value is another one. Values is something that produces individual values, but if you give it an argument that multiple values or nothing, or an empty sequence, then it's going to produce nothing as well. So, and nothing is important, nothing matters, because so in this expression, we're saying, okay, I'm looking at the value associated with the key A. I want to see if it's equal to the value that returns from the length function calling a.b. It turns out that a.b, for different reasons, I think I won't go into, always returns nothing here. So it's different reasons for different objects. And then in at.a, for each of those objects in the array, the first one, so it's returning the value a, which is 1, integer 1, but the other two values don't have a key a, and so it's going to return the empty sequence. And so in the specification, we say that for the equal operator, is that if one side is nothing and the other side is the empty node list, then they're equivalent. So I find this is a bizarre result, but this is one of the compliance test cases. So here, I don't know why you would want this kind of result, but nothing is important for this. And the other value we saw is null. So why were we putting null in there? Anytime instead of that we selected a value within the JSON query argument that was a JSON literal null, we put $null in there. And it's because in XPath, if you say, give me the value for JSON literal null, it'll say empty sequence. If I say, give me the value associated with the key A in the map, and that key A there's no key A, it's also going to return an empty sequence, so they're ambiguous. Are we up?
For you to wrap up.
All right. So that's why we have to have the nulls. So anyway, some conclusions is that I think that the combination of IXML, XPath, and XSLT really allows us to have an implementation that's close to specification, that we're able to use the template matching and higher order functions, partial function application for these kind of special things that work really well for this kind of, and I think it shows the utility of them. We're able to use non-JSON XTM data types, nothing in null. And then we can really see that the templates are close to specification. So I've got some planned updates to AJP. I'm looking for new versions of IXML to try with it. So I'm shopping around. And that's it. Thank you.
Anybody comments? Question? Ken.
I apologize. I'm going to use one of your slides to point something out to Martin, if I may.
Oh, okay. Which one?
Can you go to one of your early coding slides with XSLT and XPath?
Oh, okay.
One of the very early ones.
Okay. By the way, I'm using XSLT or XPath?
Keep going at XSLT.
Okay.
I think keep going, please.
All right. I think you're talking about the XPath ones.
Yeah,
so,
stop there, please.
So this one, so
Yeah. Oh,
here
yeah,
I am. This is an abusive notation here.
No, heavens. I was just going to point this out to Martin to say, hey, this is something that I'd like to support. In Prettier, there will be instances where spaces...
Because I find that readable.
I do too. Yeah, no. And
but it's hard to maintain.
A lot of my code...
Especially if someone else is destroying your code.
A lot of my code reads this way. And my point is that Prettier would be a risk of losing some of the information I'm trying to convey in my indentation. So.
Thanks, Ken. Okay, I think it's time for tea. So thank you very much, Alan Painter.